So now let us develop and evaluate our own chunkers. So before we start, we bring in a correspondence between this tree-like format that we see here. So we have a tree-like format where we say, okay, a sentence consists of a noun phrase, then there's nothing, and then another noun phrase, and another chunk tag format, which goes in the literature by the name of bio. And how do we make this correspondence? First, we look at the picture up here. We saw the yellow dog with its part of speech labels and then its noun phrase tags. Note here is no noun phrase tag. We can write this equivalently in this notation where we write the words vertically. We saw the yellow dog with their part of speech labels, and then here we indicate, well, this is a noun phrase, this is nothing, and this is all part of the noun phrase. Now, if we use such a notation, that is not yet unique. Why is it not yet unique? Because here we have 3 elements noun phrase, but we do not know whether this noun phrase here is a noun phrase on its own, and that's another noun phrase following here, or whether those 3 belong together, or whether there's still another combination. Maybe those 2 belong together and this one here is separate. So these 2 notations are not yet equivalent. We can make them equivalent by appending something which is called bio and stands for begin, inside, outside. So if we append this BIOs here, it's equivalent. So this tree notation here is equivalent to this information as it's given down here. And note that all we need is to indicate when something is starting a new noun phrase and when it's continuing something and when it is outside of a noun phrase. So in this notation, it's completely clear that those 3 belong together. Here's the beginning, here's the continuation, here's the further continuation. If this one here were a separate noun phrase, it would have B and P, and this one here would be the next NP, so we would have a B and P again here. So with this bio notation, we can exactly identify where are our noun phrases, where do they start, and how long do they go. Good. So as I said, there are those 2 equivalent formats. The first one, which is a mimicking, which is basically the same as this one here. So that's in text format. That's equivalent, or that's the same like this one. That is also called the Connell format. So Connell is actually a conference. It's called Conference on Natural Language Learning, Connell. And this conference, introduced this format, so people call it Connell format. It's basically a format that uses this bio notation. And there's also this tree notation where we say, okay, a sentence consists of the noun phrases and the other phrases, and these 2 are equivalent, and you can convert between them using NLTK functionality such as Connell string to tree, and there's also tree to Connell string. Now there's also a Connell corpus which dates back to the 2000s. It contains 217,000 words of the Wall Street Journal, has been divided into train and test set, and this Connell corpus is annotated with part of speech tags and with those bio chunk tags. You can look at it in NLTK by importing the Connell 2000 corpus from NLTK corpus, and you can say, go in the training file, give me the chunked sentences where you focus on the noun phrases, and let's say give me sentence number 100 or 99, and you can do it like this, and you print out, and you'll see that the sentence is as here: over a cup of coffee, Mr. Stone told his story. So and here you see, if you print it out like this, it will tell you where are the nice noun phrases that you are interested in. So now let us start out with developing some nice chunkers. And to do so, we start out as always with a baseline, a trivial chunker that is basically, well, it's not chunking at all. It's labeling everything as O. And how are we going to do this? Well, we import the Connell 2000 corpus. We make our regular expression parser that takes nothing as an argument. And then we apply this parser to the test set of Connell. We do evaluate, and we see it gets an accuracy of 43% and an F value of 0. What does it tell us? It tells us that 43% of all tokens are labeled as O, because this is exactly what our parser is doing. It's labeling everything as O. It's not discovering any NP phrases. So this is our lower bound. Now let's develop another very simple tagger that is using regular expression, and it's basically saying, well, we come up with some trivial, simple regular expression. Let's say we're coming up with a regular expression that's saying an NP chunk is everything that has adjectives, determiners, and nouns, and maybe some other part of speech labels. So we're going to come up with our grammar that says everything that starts with C, D, J, and P, and then maybe other characters such as NN, NNP, or JJ or something. And we can have multiple repetitions of this. That's going to be an NP phrase. We compile this grammar, we do the evaluation, we see the performance measure go up very nicely. Like doubling the accuracy, and the F measure goes from 0 to 70%. That's quite nice. But it's not a data-driven approach, because we as humans come up with this regular grammar with our own intuitions. And that's not typically what machine learning people like to do. Instead, they like to learn from data, because in practice, this is much more effective. So let's use our own tagger that's using some data. So what are we doing? We're going to do a unigram chunker, similar to the unigram part of speech tagger that we have developed previously. It's taking in some training sentences. It's going over all the sentences in the training sentences. And what it's doing, well, first, let's assume our sentences are in this tree format, so we convert to Connell. In Connell, we have those three elements: the word, the part of speech, and the chunk label in bio format. And we're going to keep the part of speech label and the chunk label. So we're going to use a model that is making its decision based on the part of speech label. And then we're going to use the unigram tagger that is standardly standardly implemented in NLTK. We apply it to our training data. What's that unigram tagger gonna do? Well, for each part of speech tag, it's saying the label that I will give in a new test data instance is the most frequent chunk label, right? Because we have the chunk labels here. So it's giving the most frequent chunk label, no matter in which context the word or the post tag is appearing. And then we're going to parse. Again, we take a sentence. Let's say the sentence consists of tuples of word and part of speech tags. We're only keeping the part of speech tag because this is the only information that our unigram chunker is using. We tag our post tags, and we get the tag corpus. Then what we do is we go over our tag corpus, and this again, it consists of the post tags and the chunk tags. So that's the that's a prediction from our unigram tagger. We're gonna only keep the chunk labels, and what we're gonna do is we're then gonna attach the predictions to the words and the part of speech tags in our sentence. So we use the zip function to combine the sentence with the chunk tags, with the predictions, and then we're going to make a triple out of this, right? And this is what we're going to return, and maybe we want to return it in tree format, so we're going to return the tree format again. Good. Now let's apply this to our test sentences from Connell 2000. First, we collect the trained sentences, feed this into our unigram chunker, and then we evaluate the unigram chunker on the test sentences, and we see it gets a bio accuracy. So, by the way, some people write IOP and others write bio, so this is equivalent. I prefer to call it bio. We get 93% accuracy, 83% F measure. Again, this is a quite nice improvement. In F measure, it's more than more than 10 points, 14 points even. Quite nice improvement, but we still see that this is a silly chunker, because it's just associating the most likely chunk label with each part of speech tag. So for example, determiner is always assigned BNP, and anything that is noun, starts with noun, is always assigned INP, even when it starts a noun phrase chunk, right? So we see, even though the scores are quite a nice improvement, the model is still a silly one. We can see this again by way of illustration. Here we have two identical sequences of part of speech tags, NN, VB, DT, NN, NN, point, NN, VB, DT, NN, NN, point. So those two, A and B, have the identical sequence of part of speech tags. Therefore, they would be labeled identically by our naive parser. But we as humans, or from introspection, we know that those two sentences have different different NP chunks. So the first sentence has an NP chunk here. It has another NP chunk for the farmer. John sold the farmer. That's an NP chunk. What did he sell? He sold rice. So that's another NP chunk. We can rewrite this sentence semantically equivalently as Joey sold rice to the farmer. If we rewrite it like this, you will notice immediately that this is an NP chunk and that's another one. In the second sentence, we have Nick broke a computer monitor. We only have one noun phrase chunk, namely a computer monitor. So the NP chunks differ, but the part of speech labels do not differ, so we will know that our model will make an error here. So let us now define a better chunker that is using some features that we define ourselves, and maybe one of those features will be word information. So how are we going to do this? So we're going to define a class consecutive NP chunker that we feed in some training sentences to. And then from those training sentences, we're going to create our own train set. And how does this own train set look like? Well, we go over all the text sentences in the original train set, and we're going to remove the label. So our train sentences, our original train sentences, they come with the chunk label, but now we're going to remove the chunk label using untag. Then we will also define a variable history which stores our previous decisions, or the previous code labels, so the previous chunk labels. And then secondly, now we iterate over all the words and the labels. So where the name word here is a little bit misleading, because it's actually not a word. It is just the input instance, and this could be a word or a word with its part of speech label. Below it will always be a word with its part of speech label. And tag stands for a chunk tag. So we're going to iterate over our text sentences which have the instance together with its label. We're going to extract some features from the untagged sentence at position I. So I is the position in the sentence that we are in. And we'll also take into account the history of previous chunk labels. We're also going to take the history into account, because that can give useful information what the current chunk label should be. So this function np chunk, we will define it below. So here's just something that is left unspecified that we have to define ourselves. Then what we do is, to the train set that we are creating now, we append the current features together with the chunk label, and then also to the history we append the current part of speech tag, because that's going to make up our history of, not part of speech tag, the history of our chunk tags. Once we have constructed our novel train set, where we have the features and the chunk labels associated, we're going to train any classifier on this train set. And here we choose the max n classifier, but it could really be anything. We have seen naive Bayes in this lecture. We could also use a multi-layer perceptron or any other machine learning classifier that exists. When we get in a new sentence, we're gonna use our history again. So we're gonna set up a variable history. Then we're going over all the elements, all the words in our sentence. We're gonna construct the feature set just as we do at train time. So we take sentence at position I and the history. From this we construct our feature set, and then we feed in the feature set to the classifier, so that the classifier is making a chunk label prediction, right? And then as at train time we append the chunk label to our history, and then we're gonna return the sentence together with the decisions, right? The history then is basically the predictions of our classifier. And one thing that you notice is here that there's a discrepancy between training and testing. At train time we append the gold chunk labels in our history, whereas at test time we append the predicted chunk labels in our history. That's making a difference between the training regime and the testing regime, and this will mean that our performance is not optimal. So we could try to remove this discrepancy and making training regime and testing regime more similar, but this is beyond the scope of our introductory lecture. So now we write a wrapper function, consecutive NP chunker, that is basically applying our previously implemented chunker to some specially constructed training sentences. And how are they constructed? Well, we take some original training sentences in tree format. We go over all the sentences. We convert the tree format to kernel format. And kernel format, you know that that's a three tuple of word, part of speech tag, and chunk bio label. And we're going to make pairs out of this. So the input to the classifier is a pair of word and part of speech tag, and the label is a chunk label. So this pair actually takes the role of the word here, and therefore the word is a little bit misleading. So this is not actually a word, but now as we've instantiated it, it's a pair of a word on the part of speech tag. Now when we get in a new sentence, we're going to apply our tagger to the sentence, and what we get out in the text sentence is again a pair of the chunk label, and the other element is the input, and the input is the word together with the part of speech tag. And then we're gonna, if we want to format this in kernel format, we're gonna make a triple out of the tuple, and then we can even convert back to the tree format, right? So we get a tree back, we get a tree in, and we give a tree back. Now, the quality of this approach totally depends on this NP chunk features. So depending on how we set up these NP chunk features, we get different performance. If we use as the features the following, so sentence at position I, that's a pair, as I've said, consists of the word together with its part of speech tag. If we just return the part of speech tag and make this our feature function, and then set up our consecutive NP chunker with the training data and this NP chunk features, and then test it, we get exactly the same as with the unigram tagger, because we also have the same features, right? We have the feature is basically, it's only taking the part of speech tag of the current token of the current word in the sentence into account, so we get the same performance. Good. So when we define a better feature set, we're likely gonna get better performance. So let's define a better feature set. So we take the word and the part of speech at the current position, and also we take the word and the part of speech at the previous position. So we're gonna go one word back, And then as features, we return the part of speech of the current word and the part of speech of the previous word. Of course, we could also take the word and the previous word into account, and this would give more features here. But now let's go one by one. So we only take the part of speech of the current word and the part of speech of the previous word. And note here, if we're at the beginning, there is nothing, there's no previous word before the initial word, and there's no previous pause. So we set this to some dummies. We're gonna train and evaluate our novel chunker, and we're gonna see it's getting another nice improvement, 84% F1 versus 83% before. So that's giving a nice improvement, but we can still do better and also take the current word as a feature into account, and it goes up to 86% almost in F1 and 94 in accuracy. So again, a nice improvement, and we can continue and develop again novel features. So we can return the pause, the word, the previous pause. We can also give the next pause, the next part of speech. We can take combinations. So these are independent. These are independent features. We can also take a combination of two features. Let's say the previous pause and the next and the current pause and the next pause. We can define completely different features that we just make up ourselves. So we could look at the ending of words, or what they do here is, so that's from the textbook, we can define a function that gives us what is the tag sequence since the last determiner. So determiner is like an article, the or a. What is the tag sequence? If we know this tag sequence, maybe we have a little bit of information about where in a typical NP chunk we are, right? If we see determiner, adjective, noun, maybe we're already at the end of a typical NP chunk, and we should next predict O, right? So that's why this could be helpful. If we define such a feature set, we get another nice improvement going up to 96% accuracy, 89.5% F measure. So that's really a great and nice improvement. And note here, now we have defined 1, 2, 3, 4, 5, 6, 7 features. We go up quite a bit, 5% almost, 5 points in F measure by defining 7 features versus 3 features. Now if you want to know which of those features was most influential, people are doing something that is called ablation test, where they would remove one feature at a time. So first they remove this feature and keep all the others. Then they remove these features and keep all the others, including this one, to see which of those features is the most important one. And that's what you should do in practice. Note there's another thing to keep in mind. So far in our history, we have totally ignored our history, right? So there's another variable, history, that's talking about the previous part of speech, the previous chunk text, not part of speech text, but chunk text. We've totally ignored it so far. However, it can be relevant. So knowing that we have previously said BNP increases our chance that now we see INP, right? Because usually a noun phrase chunk consists of more than one token. So after BNP, we're gonna likely see INP. Whereas on the other hand, after O, we're not gonna ever see INP, right? Because that's by definition. If there's an O, then it can continue with an O, but it cannot continue with an INP, because either there's no noun phrase chunk, or a noun phrase chunk is starting. If it's starting, it should be a BNP, but not an INP. So knowing our previous decisions can give us another boost in performance. Now they've done this here and they say there is an increase in performance. However, they don't say to what they actually compare. If they compare to this feature set, there is no improvement. There's actually a deterioration. However, it's likely, it's very likely even, that they compare to another feature set, maybe to this one here, with 3 features, and then they add also the previous chunk label as another feature, and probably they get an improvement to this condition.